Hello, everyone. I'm Bethany Sutherland, a grad student at NC State and under the advisement of Dr. Nicholas Miskidze. And today I'm going to talk to you about the radiative effects of aerosols. Aerosols are small, solid, or liquid particles suspended in the atmosphere, and they're tiny, generally 100 to 1,000 times smaller than the thickness of your hair. Aerosols have both natural sources, which are usually associated with wind-driven processes, and anthropogenic sources, usually associated with combustion-driven processes. Most of you are likely familiar with the concept of greenhouse gases in the atmosphere, which act as a blanket trapping outgoing radiation. Aerosols affect the radiation budget as well, mainly by interacting with incoming solar radiation. Aerosols affect radiation directly by either scattering it, which changes its direction, or absorbing the radiation. They can also affect the radiation budget indirectly by modifying clouds. That is not the focus of this talk. The amount that aerosols change the radiation budget is much harder to pin down than greenhouse gases. In fact, aerosols are the largest source of uncertainty in our current climate projections, and there are many reasons for this. Determining the direct radiative effect of aerosols, or DRE, would require global knowledge of the spatial and temporal distribution and physiochemical characteristics of all aerosols everywhere. This is something we're not capable of. Radiative transfer calculations generally rely on three optical properties for computing the DRE of aerosols: optical depth, single scattering albedo, and a symmetry parameter. These optical properties depend on many things, including the aerosol's chemical composition, its size distribution, shape, and location. We've had the capability of measuring optical depth remotely for a long time now. However, single scattering albedo and a symmetry parameter are much more challenging. Since we can't measure or model individual aerosols, a popular method has been to cluster aerosols into different aerosol types. So Burton et al. 2012 have developed an algorithm to classify aerosol types, such as dust, urban smoke, etc., using NASA Langley High Spectral Resolution, or HSRL, retrieved aerosol properties. Here I'm just showing an example of HSRL retrieved extinction on top, which can be used to determine the optical depth, and then types below. These were retrieved during a summertime flight in the Baltimore, Washington, D.C. area. Please note the impressive detail and variation in the distribution of types. On this day, there was mostly urban aerosols with a layer of dust around 4 kilometers and a layer of smoke aloft. So the main question left is, if HSRL can measure AOD and we can use the Burton algorithm to determine types, can we use type-specific values for single scattering albedo and a symmetry parameter? If so, we have everything we need to calculate DRE. For my NC Space Grant project, I am trying to show that using type-specific values of these parameters can lead to estimates of the direct radiative effect of aerosols, which have a lower uncertainty than other contemporary methods. So here on the left, I am showing single scattering albedo results, and on the right is a symmetry parameter. The gray shading groups the results for each aerosol type. The box and whisker plot on the left for each type shows the range in values we have derived using CATCH, which is an algorithm previously developed in our research group, which is designed to determine types analogous to HSRL types from geochem model outputs. The scatter plot in the middle of each type shows AeroNet ground retrievals for days selected to ensure that the entire column retrieval can be reasonably attributed to that type. The box and whisker plots on the right show the distribution we extracted using a spread of parameters from a variety of global climate models and me code. These figures show several encouraging things. First, we see that our catch-derived values are in good agreement with AeroNet retrievals. Second, we find that with only a few exceptions, our uncertainty from catch-derived types is lower than we get from the climate models. So our encouraging results indicate that we can likely use types and type-specific single scattering albedo and a symmetry parameter values in radiative transfer calculations to estimate the direct radiative effect of aerosols with lower uncertainty. And that is what I will be working on for the final few months of my time under the NC Space Grant. If you're interested in learning more about this work, please contact me at my email, bsuther@nscsu.edu. Thanks for listening.